It's Summer Math, easy solution. Discuss part two of my calculus of rainbow series. Look at double rainbows, how they're formed and whatnot, and the order of the colors. And basically, you could go to this site as well to see the calculations written down. You click on the link below in my info. So basically, in my previous video, I showed that if you had the rainbows are formed basically kind of like this. If you had a water particle like this, and then this is the sun's rays, and if you had a sun ray going like this, then it kind of gets refracted here and then bounces back, and then it goes to the observer here, and this is what you see. But the angle that it shows, if you were to draw the further one out here and cross this one out like that, this angle here is the deviation angle, so it's called this D. And then when D is minimum, I showed that this is when the rainbow is the brightest, or at this angle is when you could actually see it probably, and then as you get further and further or closer to it, it becomes more faint, and hence wise, if you were to have it, if you were to walk where the rainbow is, like if you were to walk all the way here, you wouldn't be able to see any rainbow because the rainbow is just an optical illusion. Yeah, so thus there's no pot of gold. So fiction. And you can only see the rainbow from specific angles, and then the brightest one is obviously when this is minimum. And I showed that this is because change in D over, if you call this angle the incidence angle, over change in alpha, this is roughly 0. So if you were to go any values, if you change this by a bit, it would still be roughly 0, so that doesn't change too much. But now the question is double rainbows, how are they formed? And so here's an image of a double rainbow. Basically, here's the main rainbow. As you can see, the colors here, it goes from red all the way to violet here in order. And then the double rainbow, this is the double one. It's on top of it. And as you can see from this one, the order of the colors are reversed. So you have let's say violet here. This is a T, violet here, and it goes down to red here, and then the question is, why is this? Well, I'll show you this one once I first show that why this one's above it. So you can see this is above the main rainbow. This one's let's call this the main rainbow. So now let's look at why it's like this. Because basically this is how some of the light rays are reflected, but it can also, some of the water particles can also reflect light a bit differently. Okay, so if this is a water particle right here, and then sometimes let's say that the sun ray first goes through here. So this is the sun ray now, and it connects at the bottom here. So because the number of sun rays are just a bunch, infinite amount of rays, goes everywhere. But then some of them that go over here around this area, this gets refracted. Yeah, this gets refracted inwards a bit differently, but let's just draw the center point here, and then draw the normal line. If you draw a normal line across like this, this is the angle of incidence, like I showed in my other video what they were. And this is sun ray, just call that. Now this one would get refracted inwards towards this normal line. So this is how it would be. This is water, so then this would go something like this, and this is the refracted ray, and then as you can see, if you keep drawing this one further, it rotates a bit like that. And this is, because it's water, this one is just, we'll call this beta. This is angle of refraction. So we'll just, now if you draw the normal line across here, call this normal because it's perpendicular to the circle here. This is perpendicular. This one is beta here, and then some of the the sun ray, some of this reflects off, but then some of the rays actually goes in, and again some of them go off here, but we're concerned with the ones that bounce back in. So the ones bounce back in, yeah, so the ones bounce back in, they also bounce back at the angle of refraction, and in this case this one will be incidence, this is refraction, they're both equal. But anyways, so if you draw a normal line across, this is a straight line. It's a bit drawn bad. And it goes like this, and then some of them again, some of the rays go out, but then some of them get refracted in again. And again, this one gets refracted. It's water, so all of them would be the same. This is the same angle there. If you draw a normal line across like this again, this is also beta. and then this one finally gets refracted outwards over here. I'll just draw this one across like that. And then once it enters air here, this gets refracted. Well, this angle here is going to be alpha again. This is the angle because it's refracted in air, and it's going to be the same one as this one here. I'll show you why later in my optics videos if I start making those. And I'll just draw a line across like this one to show that this rotated this way. And this sun ray goes to the observer. Ray goes to observer. And this is what we see. And now if we were to sum up this entire rotation, basically I'll just move this closer towards it. Or I could, I'll just draw it over here. So if you look at, if you just combine the two, this is the sun ray, and it's the final, this is the to observer. As you can see, we'll just call this one ray A, this is ray B. So if you put them in like this is A, this is B, and then if you were to, let's say the total counterclockwise rotation is this one, we'll call this D of alpha. So this is equal to, yeah, so this total counterclockwise rotation of the 4-step process, call this 4 because as you can see here, it rotates 4 times. There's 1, 2, 3, and then 4. And then if we were to just to sum it up here, this one here, as you can see, it rotates by this much. This one is equal to alpha minus beta. And then here, this if you draw this through, it rotates by this much, this ray. And this one here is just pi, or 180 minus 2 beta, 180 if you're using degrees. And then similarly, this one, now it rotates, if you just draw a straight line across this one. This one again is the same thing. This is pi over 2b. And then this angle finally here, it rotates by this much. And this one is just alpha minus beta. So if you sum all these up, we'll get the alpha, or deviation angle. This is, yeah, it's also called deviation angle. So then if you sum this up, this will be alpha minus beta plus the second one, which is just pi minus 2 beta, plus again pi minus 2 beta, and then the last one is plus alpha minus beta. If you sum all these up, as you can see here, we have 2 alpha here. This is 6 betas, minus 6 beta, and then there's 2 pi's. Plus 2 pi, so we got this one right here. And also, we also know by Snell's law, I'll show this in another video what it is, that sine of alpha of the incident angle is equal to k times sine beta, and where k is the index of refraction, and it equals 4/3 for light and water. So like before, I showed that when this is minimum, when d theta is minimum, this is when we get our brightest rainbow, or where we can see it. So this is brightest rainbow angle. And to get minimum here, well, we got to do the derivative. So we just go with, let's just write this down again. D alpha, this one is equal to, deviation angle equal 2 alpha minus 6 beta plus 2 pi. Take the derivative. This is just is equal to, well, this is just 2 minus 6, and then b prime becomes 0. And then this, because this one's number is a function of alpha using Snell's law, so then we just got to find what b prime is. I did this in another video as well, but let's do it right here. So we know that sine alpha is equal to k sine beta. So take the derivative here. This is just cos alpha is equal to k cos beta times beta prime. Solve for beta. This one for beta prime, this just equals 2 cos alpha k cos beta. And also using the trig identity, cos squared beta plus sine squared beta is equal to 1. And then rearranging this one for cos beta, we get cos beta is equal to 1 minus sine squared beta all square root. We ignore the minus sign in this case because it's plus or minus. We just ignore this one. Yeah, we ignore that because if you look at cosine just looks something like this and whatnot. And if it was negative, this would be greater than pi over 2. This is 90 degrees and whatnot, and negative 90. And from this figure here, you can see that it can't really get bigger than negative 90. Even if it goes like this, it's not gonna refract that much. So yeah, it was basically ignored because of the properties of water, and it's not gonna refract greater than this. So then once we plug this one back into this, we get, well, actually before that, we know that sine squared b. Just look at this one here, just square both sides, we get sine squared alpha. I'll just, yeah, this equals k squared sine b alpha. So then you rearrange this one. This is equals sine squared b is equal to sine squared alpha divided by k squared. Then we just plug that in here, so we get cos b is equal to 1 minus sine squared alpha over k squared. And then we plug this back in up in here. So we get b prime is equal to cos alpha over, we're just trying to get it in terms of alpha only, because this one's b there. This is, well, there's a k here, k 1 minus sine squared alpha over k squared. So now we have b prime. Now we could plug this into, well, into this equation and set it to 0. So we get d alpha is equal to 2 minus 6 times all this one right here. Yeah, so just plug that in there. And now you set it to 0. So it's set to 0, so we get 0 is equal to, I'll just put a 0 over here. And then rearrange this one, we get, yeah, we get, put this over here and divide by 2. We get 1 is equal to 3 cos alpha. We'll just, yeah, then you could multiply out at bottom. Multiply both sides by this denominator to get rid of this one. So we get, yeah, so we get this equals to 3 cos alpha. Then again, now square rooting both sides. We just to get rid of the square root. I mean squaring both sides to get rid of the square root. We get 1 minus sine squared alpha over k squared is equal to 9 cos squared alpha. And then multiply these out, equals just k squared sine squared alpha equals 9 cos squared alpha. And again, using that same trig identity, we know that sine squared alpha plus cos squared alpha is equal to 1. Rearrange this one for negative sign. Let's just put a negative sign. In this case, we'll get cos squared alpha minus 1. Just put this on the other side, equals negative sine squared. So now just plug this in there. We get cos squared plus, k squared plus cos squared alpha minus 1 is equal to 9 cos squared alpha. And now take this on the other side here. So this one will be the 9 cos squared alpha minus cos squared alpha, just 8 cos squared alpha. So rearrange this one, equals 1 is equal to 8 cos squared alpha. And then rearrange this for cos. We get cos alpha is equal to k squared minus 1 over 8 square root. Again, we ignore the minus side. And again, we remove the negative sign because it's plus or minus, right? But then we ignore it again because this one can't be less than greater than 90 degrees. Yeah, just by looking at how the figure will look like. But anyways, so we get this one here, and we know that alpha is equal to, well, this is just going to be our cos or inverse cosine 1 of square root k squared minus 1 over 8. Now, if you plug this to the calculator for a value of k is equal to 4 over 3, you get alpha is equal to, well, this is 1.2537 rads, and this is just equal to 71.83 degrees. And then, then if you plug it into the function we have, well, first we got to get beta. This one is, actually, I plug it into the deviation angle. This one is equal to 2 alpha minus 6 beta plus 2 pi. So you plug this inside to here, but then you need to know beta, and then you know that sine alpha is equal to k sine beta. So then beta is just equal to sine k, so yeah, sine alpha over k, and then this is arc sine or inverse sine. So we plug this all in here, we get a deviation angle of equals to this one is 230.98 degrees. Remember, this degrees here, not radians. So what this means is this is actually the minimum. I'll show this in an Excel graph soon. So what this means is, yeah, it means that so if you have the two rays here, so if this was your incident ray, this is the ray from the sun, and then your ray to the observer is like this one. So this one right here is gonna be 230 degrees or 230.98, and then this is your angle that we're going to be considering here. We'll just call this D2 or deviation 2, and this one's equal to 360 minus this angle, so we get 30.98 equal to, yeah, this equals 129.02. So we get this angle right here, and if you were to look at it in a large scale here, so if you have a rainbow like this one, let's just call this one a secondary rainbow, and then just say you had a primary one here, primary. So I showed in my other video that for the primary one, if you're an observer, let's say like right here, I showed that this angle across like this one, if this is parallel to, let's say, a sun ray. This is a ray of sun or whatnot. This angle right here is equal to 138, and then if you draw a parallel line across like this one to the sun ray, this one is just, well, equals to this angle, so it's 180 minus that. So 180 minus 138 equals 42. This is in my previous video. And now for the secondary one, this one is the same thing. If you draw a sun ray like this one, cross and one parallel there, this one is going to be equal to, this is the sun ray there. This is 129. And then so then this angle right here, this one would be, well, this would be this one here, so it would just be equals to 180 minus 129 is equal to 51 degrees. So as you can see, it's 51 degrees, and that's above the 42, hence you could see it above the primary one. Yeah, so thus the double rainbow is above the primary. This is just double rainbow, or the second rainbow, or the secondary or whatnot. And these are the rainbow angles. These are rainbow angles. Yeah, so then this angle's right here. So now if we look at the graph using Excel, so here's a little table I made here. So this one is K, I put 4/3, and then I made a table of the angles in degrees here, except for this minimum right here. And as you can see, these angles, alpha, this one is just equals to this times 2 pi divided by 360, just converting these angles. And so what I do here, then I scroll, yeah, do this for every single one. Then I get the beta. This one, remember, it's arc sine or sine inverse of using the alpha divided by k here. So I get the beta for every single one. Then I get the alpha here. This one is 2 times alpha minus 6 times beta plus 2 pi. Just write that here. Could even, yeah, so it's just over C4 divided minus 6 times D4 and whatnot. So all the way across here, and then I get this in degrees. I just times this by 360 divided by 2 pi. And then, so we get in degrees. This one here, this one will just be rainbow angle. And this one is 360 minus this, just to get an idea. And then from this one here, is at near 71.4, I just put in the equation for alpha at the minimum deviation angle. This one is just cosine square root. This is, yeah, k. This one is k. A4 is k squared minus 1 divided by 8. So we get 1.25. This is 71.83. And whatnot, let's get 230.98. And this is 192. 129.2. So then if we were to graph it out, well, this one is graphing out the alphas as you can see 230, so as you can see it is a minimum. So what this means that if you have angles close to the minimum across here, if you have angles slightly varying, it won't change too much, so it will be around this area. So you'll be concentrated brightness at that spot. Yeah, so what I mean by that is near that the alpha minimum, this one at 0, so this one is roughly equals to 0 when the angle of incidence is roughly, in this case, 71.3. Yeah, 71 degrees. So around 71 degrees. If there's any angles close to it, it won't deviate much. Yeah, thus you're gonna have a lot of rays coming in at a certain angle. Yeah, so a lot of rays coming at this 129 degrees deviation one, or 51 rainbow angle where you could see, and this one is this brightest spot to see the rainbow. But now the question still remains, why is it in reverse order here? So if we scroll up, why are these in reverse order compared to this one? Well, this one is opposite of this one. Well, if we look at, I put an Excel here, so I'll just go to this sheet right here. So this one is, I made it for the previous video on if you had red, orange, yellow, green, blue, indigo, violet. This is the order of the primary rainbow, and this is using your index refraction for every single one. So then I would calculate alpha according to this one. This is alpha at minimum deviation. As you can see, it's just arc sine square root. This was 4 minus k squared divided by 3 is my previous video. And then similarly calculate beta, same thing as over here. And then I get the rainbow angle. This one's 42. It gets smaller, it gets lower and lower here. As you can see, it gets smaller and smaller across here. This is highest one, so this is why red is the top. So if you had this would be red, then at the bottom would be violet here, because this is the angle that you're seeing it. This is the rainbow angle that you could see it at 40.4. But now if we look at accordingly for this is the double rainbow here. Let's write double rainbow here. This one, the top one is a primary one. Just write primary. This primary rainbow there. So if you look at in this one here, so again this is the same, add the same k values here. You could look them up online too. So 1.332. So it's close to regular light. 1.04/3 is 1.333 and onwards. But this is for colored light numbers. There's specific wavelengths of light that show visible light. And then this one we calculate alpha at the minimum. This one is going to be what we derived already: inverse cos square root k squared minus 1 divided by 8. And then this gets 71. This is the in degrees, and you could calculate beta according to that same function using Snell's law, and then calculate d alpha and then whatnot, and then you get the deviation. This one's 360 minus this, and rainbow angle is 180 minus these. And as you can see here, these are getting smaller and smaller. Bigger and bigger. So this one is actually the lowest angle is red. So now you got something like this. You got this one would be red, and this one would be violet here. This because this index refraction inverses the order now. So now it goes from here to there. So this is what you would see first. So you would see violet across here. As you can see, this is violet, indigo, and whatnot. So you get the order is reversed based on refractive index and how the double rainbow is refracted. So as you can see, yeah, the angles are opposite. Well, that's all for today. Hopefully you learned why it's reversed like this one and whatnot. Hopefully you got your head through all this algebra and angles and optics and whatnot. But this is pretty useful to know, and it's pretty interesting knowing how double rainbows and rainbows are formed. Well, that's all for today. Hopefully you learned, and stay tuned for another math easy solution.